Action.
Our group is Arc Reactor Labs, and we designed a lower extremity exoskeleton. It's an assistive device for people with disabilities. So my name is Calvin Toland.
My name is Kira Polchow.
My name is Andrew Monroe.
My name is Hilton Stallworth. So this is our initial design sketch. Our initial plan was to construct a device that would enable people with disabled legs or compromised legs to have the full functionality of a fully working pair of legs. So this includes running, jumping, squatting, bending down, you name it. And so this is our initial design sketch, and it was intentionally created to attach to the back of your lower back and connect down to your legs.
The first prototype for our device was the Mark I. And as seen on the 3D model, we used a relatively simple design that attaches to the lower back and extends from the hip to the knee. And this served as a base model for us to add to in the future. And the main function of the Mark I was to provide stabilization and support to the hip and knee area, and to be lightweight and fully functional. The main issues of the Mark I was that the hip mobility allowed only forward and backwards movement, and also it didn't contain the lower leg portion and other necessary components that we needed in our exoskeleton.
The Mark II was designed to directly address the issues we ran into with the Mark I. We improved the hip socket so you can do abduction and adduction and similar movement to a natural hip. We also changed the bolts to ensure the user without harms when using the machine. However, issues with the Mark II is that it still wasn't very stable. We didn't have any components for the knee, ankle, or foot. The shin attachment was not complete, and there's no way to attach the user to the device.
So this was our final product, the Mark III design. And some of the features and improvements that we made on the Mark III compared to the Mark II was it was a fully constructed shin support. So we basically added the lower part of the leg from your knee to your ankle. There are strap holes to secure the device to the user. You can't see it from this angle specifically, but it's on the other side. And that was at the waist brace, foot component, shin component, and thigh component. So you'd be strapped in, at all points. There was an ankle component equipped with 2 degrees of motion, to model the natural movement of the ankle. There was a foot component with a flexible toe plate for more complex movements. It was also more streamlined to alleviate excess weight to help the user, as well as optimize maneuverability. And there was adjustable thigh length for different size users. So we just tried to optimize it for all people of all shapes and sizes. And basically the goal of the Mark III was to make it as close to a natural lower body and be able to have all the degrees of motion that the lower body has in the human body.
So looking at things that we would do differently if we had more time, if we could do this whole thing over. In hindsight, our project was highly mechanical focused, which is really cool. We were able to make a really cool design with a lot of cool features and a lot of cool parts, and actually be able to simulate how a real leg would work in a mechanical setting without using bio connections like a hip joint and a socket joint. But looking at this project now, we now see that if this was to be real, we not only would need mechanical engineering, but also electrical engineering. For example, to power the thing, such as having a power source to run the motors, to have the circuitry work, and the signals and the different controls. And we'd also need computer engineering, so the code can work the machine so that it doesn't glitch out, and so it doesn't rip your legs off accidentally, because we wouldn't want that happening. And finally, we might even need some biomedical engineering. So if we have like some neural link interfacing to control the device, because how cool would it be if you just had to put on a head strap and you could walk normally, controlling with your mind. And the great thing is that all of this is possible through engineering. We may be a few years down the line before we reach that point, but I guarantee you, I'm pretty sure that it's going to get there. So that's what we would do differently if we had more time. And we hope that one day we'll be able to make it happen. So some advice from us. I'll start off. My advice is no idea is too big. You're in engineering to change the world and make it a better place. And if there's a will, there's a way. All you got to do is put in the hard work. You got this.
So some advice from me would be to definitely not procrastinate in any way. I know it'd be easy, especially when you're at the beginning of the semester and you say these things aren't due until April or May. That's really easy to say, well, I'm not going to do that until this day or this weekend. But it really is a lot of work over time. And so I really would suggest just following the deadlines, keeping up with your work, and don't procrastinate because it will catch up to you. And it'll be a very stressful couple of days if you decide not to do any of it until the very end.
Some advice for me is to get an agenda or an app on your phone to help keep track of what assignments are due when, and keep up with that. Make a schedule for yourself to make sure you don't get behind, because when you do, you're screwed.
And my piece of advice would be to do the extra credit assignments, because it's a free, 3 points to your final grade, which is typically the difference between you getting like a minus versus an A, or so it's definitely a valuable thing to do.
Most definitely. All right, guys, well, we hope you enjoyed our presentation. We've been Arc Reactor Labs, and good luck. And we're out.